In our previous tutorials, we looked at how to characterize an RF transistor through its IV curves and how to design a bias network which would fulfill specific design requirements. We also made sure by using DC blocking capacitors that no DC current would flow out of a bias network into our RF source and our RF load. This would have loaded our bias network and therefore it would have affected the bias. Equally, we looked at how to avoid RF signals flowing back into our power supply by using RF chokes. And this avoided the bias being modulated and ripples being added onto the biasing voltages, which could create instability and oscillations and possibly ultimately damage the device. We also looked at the importance of stabilizing the device, since we tried to match the input, and we saw how by using specific terminations at the input which would improve the reflection coefficient, we then ended up having an unstable output port. So we looked at different ways to stabilize the transistor, and then finally we went for a configuration which entailed having some inductive emitter degeneration, and then also some a bit of resistance in shunt with the output, which will not affect us at a frequency of operation through a quarter wave transformer, but which would help with stability at lower frequencies. Now that our transistor is stabilized, what we can do is take a look at the S parameters again and see if we can improve the gain of the transistor, the basic gain of the transistor, which is given by the S21, and achieve greater gain. So let's go to graphs, select a new graph, and then it will be a tabular graph yet again. We'll call it S parameters. So we can right click on the graph, go on to add a new measurement, and of course our data source name will have to be S parameter measurement, which is the schematic where our stabilized amplifier is. And we'll start with putting on our S21 measurement, and that represents the basic gain of the device in its current configuration. We'll also display it in dB, because this is the most customary way to display the gain of a transistor or an amplifier. So we'll just pick magnitude and we'll select dB as the units, and then click on apply. Then of course we want to see our reflection coefficient at the input, which is S11, but we won't have it in dBs, because for some of the calculations that we need to carry out, we need to have it as a normal decimal number. Click on apply. And then we'll have our output reflection coefficient, which is S22. Again, we'll just have the magnitude for now, and in decimal, click on apply. And then we'll have our S12 as well. We haven't talked about this parameter as much as the others so far, but in this tutorial we will, because this is a very important parameter when it comes to the design of amplifiers. Click on apply, and then OK. Then simulate. You can see that we've got the same basic gain that we calculated in a previous tutorial, which is 11.8 dBs. You can also see that our input is considerably mismatched, considering that the absolute value of S11 is 0.47, and also S22 has got quite a considerable mismatch, with an absolute value of about 0.76. So what we can do now is try to match the input and the output of the transistor, so that the transistor sees terminations which are much closer to the conjugates of its own input and output impedances, and then we'll have less power reflected, and theoretically we should increase the gain. Now the important issue is here that we cannot actually consider the input and output ports, and hence the input and output impedances, as separate, because our S12 is not 0. The S12 gives you a measure of the interaction between input and output. So you've got a parameter that shows you how much power can flow back into the input port from the output port. And this means that whatever you connect at whatever side is going to affect then what's going to happen to the currents and voltages on the other side. And hence, because as we know impedance is the ratio of current and voltage, we'll see a change in the output or input impedance depending on where we've connected a termination. However, just for an experiment and to see how much of a compromise we will make if we ignored S12 and assumed that it was actually 0, we will just go through what's called a unilateral match and see what we can achieve. With a unilateral assumption, you're assuming that S12 is 0, and hence you have minimal interaction between your input and output, and the terminations that you connect to the input won't affect the output, and vice versa. So you can consider the input and output terminations of the transistors as separate. You look at what they actually are, you look at their complex conjugate and try to connect to the input the complex conjugate of the input impedance of the transistor, and to the output the complex conjugate of the output impedance of the transistor. So let's try to have a pictorial representation of what's actually going on. We've got a basic transistor which is biased and stabilized and has got a basic gain of G0, and that would be the S21 that you see at the moment, which is 11.8 dBs. We also have an input reflection coefficient represented by S11 and an output reflection coefficient represented by S22. From those, as we know, we can get the input impedance of the transistor and the output impedance of the transistor. Then you've got the S12, which shows you the power that flows back into the input from the output. Now, if we assume that S12 is very small, we have a situation whereby the transistor input and output are independent, and so we can add an input matching network to increase the gain by a certain amount, and an output matching network to increase the gain by a certain amount. Now, how much can you increase the gain is dictated by how much mismatch you actually have. So if your input is seriously mismatched, for instance, then the S11 will be quite big, and we have a formula that helps us work out what is the maximum improvement in gain that we can achieve based on the value of the S11 magnitude. So the formula is shown here, and it's basically telling us that the bigger the S11, the more we can gain by matching the input of the device. Similarly, we can look at the output reflection coefficient, and we have a very similar expression which tells us how much we could gain by matching the output. So what we have effectively is two little dials at the input and the output, and we can tune these dials by changing the input and output matching networks to achieve the required gain. So you've got the basic gain of the transistor, which is G0, then you've got the gain which you get from inserting an input matching network, which is GS, and its maximum value is what we've shown with the previous formula. And then similarly, you've got an output matching network which you can adjust to achieve a maximum increase in gain of the value which we looked at before. So we can see that through the input matching network we can at most increase the gain of the transistor by about 1 dB, whereas through an output matching network we can increase the gain of the transistor by over 3 dB. So if we were to choose between one and the other, it'd probably be more worthwhile to go for the output rather than the input. Sometimes the gain increase is minimal for one of the two ports, in which case there's no point in actually bothering matching the port at all. So let's get cracking with this and design an input matching network to start with and see what kind of advantage this gives us. So we'll just go to circuit schematics and open a new schematic. We'll call it input match. And so what we want to do with this matching network is transform the 50 ohm source impedance into the complex conjugate of the transistor's own input impedance. So we'll start by putting our source impedance in, which will be a simple resistor which has got a value of 50 ohms. Then we'll put a ground connection at the end of that, and then we'll insert also a measurement port by using Ctrl P, which allows us to see the impedance which our matching network presents. Then we can go to graphs, add a new graph, and in this case it will be a Smith chart, and again we'll call it input match. Then, as usual, as a first step, we'll have to change the appearance of our chart. So we'll just right click, go on to properties, and then we'll go on to format, and we'll choose the impedance lines to be green, the admittance lines to be red, and then we'll go on to grids, and we'll get both impedance and admittance grids. We'll take the values off and select the contour density to coarse. Click on apply and then OK. Then what we want to display on here is our target impedance, which is the S11 conjugate taken from the transistor schematic. So we just right click, go on to add a new measurement. We want the S11 from the schematic which has got our stabilized transistor, but we don't want to display its value. We want to display its complex conjugate value so as to be able to achieve the perfect match between what we connect to the input of the transistor and its own impedance. Click on Apply. Now we need to add a new measurement which allows us to see the impedance of the combination of a matching network and our source impedance. This time the data source name will be the input match schematic. We want to see S11 yet again so we can see the impedance, but we must make sure that in this case we just represent the normal complex value, not the complex conjugate. Click on Apply and then OK. Then Simulate. Now you can see that we've got our source impedance right here and our target impedance right there. We could carry out the match in a number of ways. One which is very obvious would be using a series capacitor first, which would take us down the unity constant resistance circle to the point where it intersects the relevant constant conductance circle, and then from there we can add an inductor in shunt to reach the desired point. However, because we are working at a relatively high frequency, which means that our wavelength is relatively small, it is advantageous in this case to use transmission line matching. And it is also very instructive for you to understand how it is done in a practical case. And there are a couple of tricks which I'd like to show you. Implementing an L-section matching with transmission lines entails using shunt stubs, and these can be either open-circuited or short-circuited. In this case, let's use open-circuited stubs to begin with. So if we added an open-circuited stub in shunt with our load, this will move us down the constant conductance circle, and then we'd have to add a stretch of transmission line to rotate around the chart and reach our target point, which is the conjugate of S11 for our transistor. So as you know, when we add a stretch of transmission line, we move in a clockwise direction on a circle which is centered on the center of the chart and which has got a radius which is equal to the modulus of the reflection coefficient of the target point. In this case, the conjugate of S11 for our transistor. So ideally, what we'd like to be able to do is draw a circle which is centered on the Smith chart and then has got a radius equal to the modulus of the conjugate of S11. Can we do that? Well, we can in Microwave Office, but we have to go about it in a slightly circumvented way. In Microwave Office you don't have constant gamma circles, but you have constant VSWR circles. We looked at VSWR in our manual and in previous videos, and we've seen how VSWR is related solely to the magnitude of the reflection coefficient by the formula that is shown here. So effectively, since to draw our circle all we need is the modulus of our reflection coefficient, and since VSWR is directly related to the modulus of the reflection coefficient, we could equally use VSWR circles or gamma circles. We just need to carry out the conversion between one and another. This is not as hard as it may sound, since VSWR can be given to you by Microwave Office directly. But it is harder to talk about it than to do it. So let's go back to our S-parameter table and then right-click and add a new measurement. And in this case, we'll go to the linear measurements and we'll choose VSWR. And we'll choose the VSWR which comes from our S-parameter schematic. And we'll choose the port as port 1, because of course we want to see the VSWR at the input. Click on Apply and then OK. Then Simulate. So we can see that VSWR is approximately 2.76. We can go back to our input match Smith chart, right-click, go on to Add a new measurement, and in this case, under the linear heading, select Circle. And then we can choose VSWR circle. So a VSWR circle is a circle which has got a constant VSWR, which also means that it's got a constant gamma, a constant reflection coefficient magnitude. So what we can do now that we know the value of VSWR which relates to our S11, we can just type the value here, 2.76, and then click on Simulate. And as you can see now, we've got a circle drawn, which is exactly the circle that we wanted. A circle with a constant reflection coefficient magnitude, which allows us to then carry out our match in a much easier way. Remember that S11 conjugate and S11 have got exactly the same modulus, they just differ in phase. So now we've got this constant gamma circle, which we've managed to obtain from a constant VSWR circle. And what we can do, now that we know the intersection between the constant conductance circle and the constant gamma circle, is add an open-circuited stub to get to this point first, and then a stretched transmission line to get to our final point. So let's get started. Let's go back to our schematic, input match, and then we press Ctrl L and add an open-circuited stub, and we put it in shunt with our source impedance. Then we set the frequency of operation to 1900 MHz, and we'll make the length of this stub as 0 as an initial value, but also we'll make it tunable. In fact, we can also set the range over which we want to tune by double-clicking and then selecting a minimum value, say 0, a maximum value, say 180, and a step, let's say 1, and then enabling the limits. Click on OK, and then simulate. Let's go back to our input match. Of course, nothing has changed because we have an open-circuited stub of 0 length. So now let's open the tuner and let's start tuning to a point where we meet the constant gamma circle. So we can see that when the stub is about 46 degrees in electrical length, we've reached the intersection between the unity constant conductance circle and our constant gamma circle. So now we can close the tuner and go back to our schematic, and then we can insert a transmission line in series so that we can get to our desired point, which is the conjugate of S11 for our transistor. So we'll set the frequency of operation here yet again to 1900 MHz. We'll double click on the element, we set an initial value of 0, we make the element tunable, we set some limits between 0 and 180, which allows us to go all the way around the chart, use a step of 1 degree, click on OK, then simulate, and let's go back to our input match graph. Of course we haven't moved because the initial value for the length is 0, so let's open the tuner now and let's start increasing the length until we get to a point where we are pretty much overlapping the conjugate S11 for our transistor. So let's close the tuner, let's go back to our input match schematic. First of all, let's flip the schematic by pressing Ctrl A to select all the elements, right clicking, selecting flip, and then drawing the axis about which we want to flip. The reason why I've done this is because I want to give you a better visual idea of what we've done here. We've got our source impedance here, which is 50 ohms, and then we've got a matching network here, which transforms our 50 ohm impedance into the complex conjugate of S11 for our transistor. So what we see here is the S11 conjugate for the input of our transistor, and hence now we should be able to achieve a very good match between source and transistor input, minimize the reflection coefficient S11, and hence possibly increase the gain. Remember, however, that the gain should not increase by any more than 1.08 dB. So let's verify this. First of all, I don't want to meddle with the S-parameter measurement schematic, so what I'm going to do, I'm just going to right click on it and create a copy of it, then rename this copy something like S-parameter matched. And now we've got a copy of the schematic that we can use to insert the input matching network first and then the output matching network later and see what advantage we get. So let's go back to the input match schematic and then select our matching network, press Ctrl C to copy it, and then go back to the schematic, make a little bit of space here, and then space our matching network in series with the input of the transistor by pressing Ctrl V and then placing it. Then we can reconnect everything else. Now we need to set up a new graph so that we can get the S parameters from this new circuit. So let's set up a new graph and we'll choose a tabular form yet again, and we'll call it S parameters matched. And then we add the same measurements as we added before to the other one. So go to add a new measurement, and then we'll choose S parameter matched as the source. We'll have the port parameters, S parameters, and then we'll have S21 first as a magnitude in dB. Click on apply. Then we have S11 as a magnitude. Then we'll have S22 again just as a magnitude, and then we'll have S12 also. Click on apply and then OK. Then simulate. Now what we can do is go to Window, select Close All, and then just reopen the two windows which have got S-parameters on them, one for the matched transistor and one for the transistor unmatched. And then we can select again Window and Tile Horizontal, and this way we can directly see a comparison between the two sets of S-parameters. Let's resize these windows a little bit. And you can see that we started from 11.8 for the S21 and we got up to 12.85, which means an increase of 1.05 dBs. This is very much in agreement with the maximum value which we calculated, which was 1.08 dB. And then you can see that the magnitude of S11 has also decreased considerably. However, notice that the S22 parameter has now changed. So we've gone from having 0.76 to having 0.73 as a magnitude for our S22. Also, for the S12, you can see that things have changed to some extent. Now, when we do our output match, we can no longer use the S22 which comes from the schematic which has got the unmatched transistor on, because things have changed. So the S22 and hence its conjugate, which we will be using to carry out the output match, will need to come from the new schematic where the input is matched and the output isn't. So let's crack on and try to match the output and see what improvement we get. So let's go to Circuit Schematics, right click, open a new schematic, we'll call it Output Match, and then we'll start with our load impedance and we'll put a ground connection there. Our load impedance will also assume to be 50 ohms, and then we'll have to add a measurement port here so that we can see what impedance is presented by our load impedance and the combination of our load impedance and the matching network once we put it on. Now let's go to graphs, and instead of setting up a new graph from scratch where we have to change all the appearance on the chart, etc., what we can do is just duplicate the input match graph and then change the measurements that appear on it. So you can just go for duplicate graph, and then we'll rename it, of course, as output match, and then we have to change all the measurements on it, of course. To do so, we have to right click and go to modify measurement. First of all, the S11 conjugate must change to S22 conjugate, because now we're matching the output. But also, it'll have to come from the matched transistor schematic where the input has been matched, because as we said, the S22 has changed. This is due to the fact that the unilateral assumption in this case doesn't strictly apply, so you can't really consider the two ports independent. So we've modified the measurement as we wanted to, and then click on OK, and then we can again right click, go to modify measurement, and we want to see the S11 from our output match schematic, and then click on OK. And then finally we need to change this VSWR circle, because now we want a constant VSWR circle which corresponds to a constant gamma circle which has got as a radius the modulus of the S22 conjugate. So we can either calculate this manually or just simply go to the S-parameter table, make sure that you're looking at the one that comes from the matched transistor, the transistor that's got an input match on it, right click, go to add a new measurement, and then go to linear and select VSWR, and then choose the S-parameter matched as a source and the port index to be 2. Then click on apply and OK. Then simulate. Now you can see that the VSWR at the output port is about 6.33. So we can go back to our output match graph, and the only measurement left to modify is the VSWR, for which we just have to change the value and set it to 6.33. Click on OK and then simulate. Now you can see what we've got here. We've got the S22 conjugate displayed on the graph, and this is the impedance we want our transistor to see to maximize power transfer. We've got a load impedance which is 50 ohm, and we've drawn a constant VSWR circle which also in turn, as we've seen, represents a constant gamma circle which is centered in the center of the chart and goes through the conjugate S22 point. So yet again, for consistency, let's start with an open-circuited stub. So let's go back to our schematic and add an open-circuited stub in shunt with our load. Set the frequency to 1900 MHz, and then let's make it tunable. Select an initial value of 0 and limits between 0 and 180 degrees in increments of 1 degree. Now let's go back to our graph, click on Simulate, open the tuner, and then you can start increasing the length of your stub until you get to a point where you intersect the constant gamma circle. So we've worked out the value of our open-circuited stub in terms of its electrical length, which is 65 degrees. Now we can close the tuner, go back to our schematic and add a transmission line in series with our matching network. Again, we must set the frequency to 1900 MHz, and then we can connect it to the port, double click on it, make it tunable, start from 0 and select a range between 0 and 180 degrees in steps of 1 degree. Then simulate, and let's go back to our chart. Now we can open the tuner and we can start increasing the length of our line until we get to the desired point, which is the conjugate of S22. So we've got a transmission line of 93 degrees in electrical length. Now let's close the tuner, and again let's go back to our output match schematic. In this case we've started from a load impedance of 50 ohm and we've used a matching network so that at this point here, which will be the output of our transistor, what we see is the S22 conjugate for the transistor. So again, let's select these two elements, press Ctrl C to copy them, and then go back to the S-parameter matched schematic and make a little bit of space for ourselves. And let's insert our matching network right here by pressing Ctrl V and then placing it. Now let's simulate and let's see what's happened to the S-parameters. Well, you can see that the gain has increased considerably and it's gone up to about 16.11 dB. So we've improved the gain considerably, and now our S22 is quite low. But look at what's happened to S11. S11 has gone up quite a bit. So what we've done here is we matched the input and this changed the output slightly. Then we matched the output and then changed what happened at the input by quite a lot. So it looks like if the S12 is not 0 and is a significant value, then you would have to go through quite a long iterative process to optimize the matching network at the input and output until you get the desired values. And that really isn't ideal, because effectively you're relying heavily on an iterative process. So when you have an S12 which is not 0 and is significant in value, it's much better to use different techniques if you want to maximize your gain. And we will be looking at other techniques in the next tutorial, and we'll see how we can use some mathematically worked out values which allow us to calculate the input and output matching networks at the same time, so the calculation takes into account the interaction between the input and output. And you put these two on together rather than one by one and achieve the maximum gain for your transistor. So we'll be looking at this technique, which is called simultaneous conjugate match, in our next tutorial.